Hey guys, let's talk about electric field. Okay, but before we do that, let's talk about something that you are more familiar with and connect the idea of that with this new idea of electric field. So suppose you have empty space with nothing in it, and then you introduce a mass m into space. Okay, so first question is, would this mass go anywhere? Would it move? The answer is no, because nothing is exerting a force on it. Okay, so if there was another mass in space, then the two masses would be attracted towards each other, and then they would move towards each other. Okay, but here there's only one mass, so it won't go anywhere. Okay, but compared to the situation when there was nothing in space, and now that there's a mass in space, has something changed? The answer is yes. Okay, the presence of this mass is creating gravity. Okay, and because of the gravity that this mass is creating, if you were to introduce another mass, then that mass would be pulled towards this mass because of this mass's gravity. Okay, so this let's call this m1, and m1 is creating gravity at this moment. And then if you were to introduce another charge m2 in space, then because of the gravity that m1 is creating, m2 is going to be attracted towards m1. Okay, and then same thing with m2. m2 creates this gravity, and then because of the gravity that m2 creates, m1 is attracted towards m2. Okay, so force on m1 is equal to m1 times gravity created by m2. Okay, and force on m2 is m2 times the gravity created by m1. Okay, and another way of writing that is m1 times, and remember gravity is gravitational constant, times m2 over r squared. And this you can rewrite as m2 times g m1 over r squared. And they're both the same thing, as you would expect, because the forces are equal and opposite on these masses. Okay, so this part is gravity. Okay, and this part is gravity. And then when you multiply gravity with the mass, you get the force. Okay, so electric field is similar to gravity. Okay, so you can make almost the exact same argument for electric charges. Okay, so suppose you empty out space. Okay, there's nothing in space, and you introduce a charge q. Okay, now would this q go anywhere? No, it won't go anywhere because there's nothing exerting a force on it. But if there was a charge, a second charge, then this q1 and the second charge could either attract or repel each other depending on the charges, and then they would move. But just by its mere presence, what is it doing to the space around it? Okay, it's creating something analogous to gravity. Okay, and it's called the electric field. So it's creating the electric field, and because of the electric field that q1 is creating, if you were to bring a q2 here, then q2 would feel a force because of the electric field that q1 creates. Okay, and by the same argument, the electric field that q2 is creating is going to exert a force on q1. Okay, so another way you can say that is that force on q1 is equal to q1 times the electric field produced by q2. Okay, and then force on q2 is equal to q2 times electric field produced by q1. Okay, so and another way of writing that is, remember, so force is k q1 q2 over r squared, so q1 is this, times k q2 over r squared. Okay, r squared is this distance, and here it was this distance. Okay, and this would be Q2 times K Q1 over R squared. Okay, so this part is the electric field produced by the second charge. This part is the electric field produced by the first charge. But force, of course, is the same because it has to be equal and opposite. Okay, so electric field is nothing but force divided by the charge that the force is on. Okay, so force was K times Q1, Q2 over R squared, but electric field is just KQ over R squared, okay, without the Q. And then if you wanted to find the force on some charge, then you multiply the E by that charge, and that would give you the force. Okay, I hope this is clear.
So we just discussed that the magnitude of the electric field by a point charge is equal to kq over r squared. Okay, and electric field is a vector. So let's talk about the direction of the electric field. So suppose you have a point charge plus q. Okay, then the way you figure out the direction of the electric field that is produced by this plus q is you take a very small positive charge and you put it somewhere in space where you want to find the direction of the electric field. So say you place it here. Then since this small charge is a positive charge, then it's going to be repelled by this charge. Okay, so what happens if you place it here? It's going to be repelled. If you place it here, it's going to be repelled. Place it here, it's going to be repelled. Okay, if you place it here, it'll be repelled. Place it here, it'll be repelled. Here. Then, so it's going to always go radially away. Okay, doesn't matter where you put it. So you can put it anywhere along this line, so you can make it a continuous line from the charge. Okay, so this is what the electric field pattern for a positive point charge looks like. Okay, so what if you want to find the direction of the electric field produced by a negative charge? Okay, so suppose you have a negative charge here. Okay, and you test the direction of the positive charge with a, and you test the direction of the electric field always by a positive charge, a positive test charge. Okay, so again, you're going to take a positive test charge and you're going to place it all around in space to figure out the field pattern of this negative point charge. So let's say you place your positive charge here. It's going to be attracted to the negative charge in this direction. Okay, place it here, it's going to be attracted. Place it here, it's going to be attracted here. And doesn't matter where you place it, it's going to always be radially attracted to the negative charge. Okay, so the direction of the arrow represents the direction of the electric field. Okay, so this is how you figure out the direction of the electric field for point charges. So now, suppose you had a point charge here of magnitude q and another point charge here, magnitude 2q. Suppose they're separated by distance r, and you wanted to find, and suppose this one is plus, suppose, and you wanted to find the electric field at this point P, that is a distance r from this plus 2q. Or you know what? Actually, let's make it negative. So this is negative. Then what is going to be the direction of the electric field at P? Okay, then the way we're gonna find the electric field at P is we're going to use superposition. Okay, and we're going to find the electric field produced by negative 2q at point P, and then we're going to find the electric field that's produced by this plus q at P, and then we're going to sum it using vectors. Okay, so what is going to be the direction of the electric field due to this negative 2q? Okay, so a positive charge would be attracted towards the 2q. Okay, so this is going to be the direction of the electric field due to the 2q. Okay, what about the direction of the electric field at P due to this plus q? A positive charge, the positive test charge at P is going to be repelled by the plus q. So the electric field due to the plus q is going to be to the right. Okay, and then the total electric field would be EQ minus E2Q. Okay, and when you plug in the given parameters, you're gonna end up getting KQ over 2R squared minus K times 2Q over R squared. Okay, so that would give you the direction of the electric field at P. So, and because negative 2Q is a larger charge, and also the separation between the negative 2Q and P is smaller, then when you add up the electric fields, you should get an electric field that points to the left. Okay, so now that you found the electric field, suppose there actually was a charge at point P. Suppose there was some charge, big Q at P. Then how would you find the force on that Q? Okay, so we know that force is equal to charge times the electric field, right? So we found the electric field, and we know that our given charge is Q. So Q times the E total that we just found would give us the force on the Q. So a quick remark on the problem that we just solved. Suppose that you wanted to find a point somewhere along the line that joins these two charges where a charge would not, where you could place a charge so it doesn't move. Okay, so if you want to place a charge somewhere so it doesn't move, that means the net force on that charge has to be 0. Okay, and so if the net force on the charge has to be 0, then this implies that the total electric field at that point has to also be 0. Okay, so where can that point be? Can that point be somewhere here? Okay, so what would the electric field be somewhere in the middle? Okay, so a positive charge here would be repelled by Q, and it would be attracted by 2Q. So the electric field is always going to be pointing to the right, no matter where you place it. So electric field cannot be 0 in the middle of these two charges. Okay, what about here? So here, the positive charge would be attracted towards the negative 2Q. It would be repelled by Q. But the thing is that the attraction due to 2Q is going to be much stronger because this charge is stronger, plus this distance is smaller. So it cannot be here. What about here? Okay, in this case, it's going to be repelled by Q and attracted by the negative 2Q. But now it's possible that the attraction and the repulsion can balance themselves out, because even though Q is smaller, now this point is much closer to Q. So it's possible to have electric field 0 in this region, and the way you would find it is, so this is some unknown distance x. Okay, so you would say that the electric field at this point, so we're finding the electric field at point P is going to be kq over x squared due to the positive charge, and due to the negative charge it would be k times 2q over r plus x squared, and you would set it equal to 0 and then get your x, and that would be the point where the electric field on the electric field would be 0, and therefore if you place a charge at that point it would not feel a force and it would not move. Okay, so now let's do a problem that is slightly more complex. So suppose you have a charge q here. Okay, we've seen something like this before, and another charge 2q here, r. Okay, suppose this is also r, and this is a charge, this is negative charge, and suppose this is 3q, and you want to find the electric field at this point P. Okay, and this is r, and this is also r. Okay, so then what okay, so let's do the directions first. So this 2q is the electric field due to that q2 is going to be downwards, straight down like this. Okay, and again we're going to be using superposition. Then, and the electric field due to this q is going to be, a positive charge is going to be repelled. Okay, and then electric field due to this negative q is going to be in this direction. Okay, so to find the electric field at P, we need to find the electric field, the x component of the electric field, and the y component of the electric field. Okay, so we need to break this into components. Okay, so when you break that into components, its x component is going to be here, and the y component is going to be here. And again, this is going to be 45-degree angle. Let's call it theta. This is theta. And then this side is going to be square root of 2r, right? Because this is square. So, okay, so the electric field in the x direction is going to be kq over square root of 2 times r squared cosine theta minus k times 3q over r squared. Okay, and the electric field in the y direction is going to be kq over square root of 2 r squared sine theta, and plus, because they're both going down, k times 2q over r squared. Okay, so that would give you the electric field, the x and y components of the electric field at point P. And to find the magnitude of the electric field at point P, you would say the x component of the electric field square plus the y component of the electric field square root. Okay, so next video we're gonna wrap up electric field and do some integration problems. See you then.